In this video, we're going to be going over basically some notes on electric charge to kind of get an idea of how they work and what they can do for us in electricity and magnetism. Okay, so when you start up the assignment, you've got a video that kind of walks through some of the important stuff, has some good visuals. You've also got some links to simulations that you'll see throughout the assignment that can be good to kind of see the things and actually kind of give you a better idea of what happens in the very, very tiny world of atoms that causes charges to push and pull on each other. Okay, got a couple attempts. Let's start one. Okay, first page just has a link back to the video, and again, links to the simulations that you can see as you go through the assignment. Okay, so to start us off, electric charge is a property of subatomic particles, which are the little bits of atoms that everything's made of. And those little electrically charged subatomic particles are what allow static electricity and electric current to happen. It's what causes chemical bonding, and basically it's the core of chemical reactions. It's why things change in the first place and how they change from one substance to another. If you want to get really nitty gritty with it, then you can also say that electric charge is really responsible for just about everything that happens on Earth besides forces of gravity. Just about everything that happens with pushes and pulls, even on physical contact, comes down to electric charge, because really we're just made of a bunch of little charged particles. But we're not going to go into that. That's kind of a deep dive for another day. When we measure charge, we use the unit of Coulombs. Coulombs right there. Its symbol, or its abbreviation, is big C. Okay, like this. Okay. So whenever we measure an amount of charge, we measure it in coulombs, and it's typically a very, very small amount of charge because we're dealing with very, very small particles. Now you can scale up an amount of charge to have like a whole bunch of it, so it's something that we can conceivably measure. But something like 10 coulombs, which doesn't seem like a big number to us, is actually a huge amount of charge. So it kind of feels a little weird to keep track of such small numbers. We usually end up using a lot of scientific notation, as we're going to see here below. Okay, so one way we can kind of simplify how we show charge is by using something called the elementary charge, okay, which is this little e here. So that little e stands for the most reduced down version of charge that we can get. Like, your charge can only really get so small in the physical world that we're going to use in this class. So we can take that really, really tiny number of charge and reduce it down to something that's a lot easier to manage. Okay, that small number that we get of charge that can't really get any smaller is this 1.6 times 10 to the negative 19th coulombs. Okay, so that would be like 0. And then like 19 zeros, and then like 1/6, or I guess it would be 18 zeros because you're going to be skipping past this part, something like that. But it's going to be like a lot of zeros, and then finally your 1/6. It's very, very, very small number. Like, most of your calculators won't even be able to handle it without scientific notation because it will fill up your entire screen. So instead, we call that 1. We call that 1 elementary charge, okay, or just 1 charge in general. Okay, so instead of measuring it out in coulombs like you'd measure distance in meters or mass in grams, instead of measuring out in coulombs, we sometimes just say it's this much charge, 1 or 2 or 3 or -1 or -2 or -3 and things like that. So the smallest bit of positive charge that we run into is going to be +1 of your elementary charge. Okay, and we get that from protons in the nucleus, or the center of atoms. Okay, protons are your positively charged particles that the universe is kind of built on. It's one of the subatomic particles in the atom. Okay, we also have electrons, which are outside the nucleus, outside that center of the atom, in something called the electron cloud. That's where our negative charge comes from. Okay, so one proton has a charge of +1, and one electron has a charge of -1. And of course, that means actually a charge of positive 1.6 times 10 to the negative 19th coulombs, or negative 1.6 times 10 to the negative 19th coulombs, but those numbers are kind of nasty to deal with, so we're going to avoid them as much as possible. And it doesn't really help us much to deal with them directly. If we can avoid it, we will. Okay, if you want to get an idea of kind of how much charge something takes, a camera flash takes about 0.025 coulombs, which doesn't seem like a lot, but maybe a camera flash doesn't seem like a whole lot of energy would be required anyway, so maybe not a lot of charge is required to get that to happen. Um, but if you think about how many electrons it takes to get that much charge, it take 100,000 trillion or 10 to the 17th electrons to get that done, which is kind of wild. Okay. On the other hand, a lightning bolt takes about 15 coulombs, which again is a pretty small number to us, but that's like 600 times more electrons and 600 times more charge as it would take in this case of a camera flash. Okay, that's like a bunch more. Okay, so even though this coulombs amount is a small measurement, we're talking about a lot of particles that can make up that small itty bitty amount of charge. Okay, so we have really, really high amounts of charge. That's coming from a ton of charged particles that our matter is made of. Okay, so here's a depiction of an atom where you've got your protons in the middle, in the nucleus, in the center of the atom. Those are positively charged, and your electrons are somewhere out there in this little bubble, this little cloud. They have a -1 electric charge, a -1 elementary charge. Okay, so let's go on to the next page. Okay. Now, these electric charges, whether they're positive or negative, are going to have certain pushes and pulls on each other. But when they're close enough together, we kind of just sum them up. In other words, positives kind of affect other charges one way, and negative charges affect things kind of the opposite way. So if they're close enough together, they kind of cancel each other out. You can kind of think of it like if you're applying two forces that are same strength but in opposite directions to each other, you don't get any motion. Like if your friend is pushing on a box with 5 newtons of force and you're pushing on the other side with 5 newtons of force, it's not going anywhere. So when you have positive and negative charges grouped together in something like an atom or even in a large object, we kind of look at the total charge of positive and negative that can cancel each other out. Okay? In other words, we call this the net charge. Okay? If you were to total all that charge up of positive and negative, you get the net charge. And that's what we look at of how something can push or pull with electric forces. We only look at the net charge. So, for example, that atom of hydrogen that we saw in the previous page had 1 proton and 1 electron. Those are both charged particles. But together in the atom, that +1 and that -1 charge cancel out. +1 and -1 added together makes 0. Okay, so overall, something that has a bunch of positive and negatively charged particles can be electrically neutral. Okay, in other words, it's not really acting positive, it's not really acting negative. All those charged particles are still there. They don't like annihilate each other and disappear forever. They're still there. But it kind of seems like they aren't there because we've negated the forces that come from them. Okay, which is why we don't really have things constantly flying through the air and sticking to us like static and things like that. It only happens in some very specific situations because most of the matter we're dealing with has the same number of positively charged protons as negatively charged electrons, and so there's kind of a balance between it. Okay. Now, when you do have something kind of pushing or pulling on something with electric forces, that comes from having a net charge that is positive or negative. When you have a little bit more positive or a little bit more negative charge, that causes some push or pull on things. That isn't canceled out when you add them all up in the net charge. Okay, so for example, sodium chloride, or table salt, is a compound, and it also can be found as a mineral. And down on the atomic level, sodium chloride is basically atoms of sodium and atoms of chlorine that stick together because of electric forces. So we have an atom of sodium and an atom of chlorine here. The positive charge from the protons is in the center of the atom, in the nucleus. And instead of showing out each one, we're just saying like this has +11 and this has +17. So that's saying we have 11 positively charged protons, each with the charge, an elementary charge of +1. All these have a charge of +1 also. They have 17 of them. Okay. And these blue guys on the outside are the negatively charged electrons. So a sodium ion has 11 protons and 10 electrons. Okay, when it goes and sticks to this chlorine atom, it loses an electron. Okay, so if we compare the 11 positively charged protons to the 10 negatively charged electrons, well, positive 11 plus negative 10 leaves us with a little bit extra positive charge. Okay, so this sodium atom is actually going to end up with a positive charge. We call that an ion. Okay, it's still an atom, it just has a charge. So a charged atom is called an ion. Okay, a chlorine atom ends up with 17 protons in the middle and 18 electrons. It kind of picks up an extra electron. So it ends up with a charge of, well, positive 17 and negative 18 smashed together means you're going to have a little bit extra negative charge in this case. So your net charge is going to be -1 instead of +1. Okay, if you want to see how this works, you can use this simulation here. Put the toolbar away. Okay, so this is your atoms separate from each other. And if you click on ionization and ionic bond, you'll see the electron move. And then you end up with charged things where you have an imbalance of positive and negative charge. That causes an electric force that brings these together. Okay, and you can also try this with a bunch of other different combinations of atoms, which is kind of fun. So you can see like that come together. That's kind of cool. Okay, so let's go back to here. Okay. Oh, I lost my mouse. Oh. There we go. Oops. Okay. So let's go on to the next page. All right. Now, electric forces are kind of like gravity in the sense that they can work from a distance. They have what's called a force field that shows kind of where all the points in space are being forced or pushed and pulled on. Okay, so a force field kind of sounds like a sci-fi topic, but it's actually a concept in physics. It's real that shows us the vectors of force in all points of space. And remember, a vector is just something that points in a direction and tells you how much force is going on there by having a longer or shorter arrow. Okay, or it shows the strength of the magnitude of the force. Okay, it's like this is a force field. It shows you have something, some dot in the middle here that's causing a force inwards towards it. And so wherever something would be in this point of space, these arrows would tell us how much force would be applied to it on something like that's maybe here, or something that's here, or something that's here. Okay, when we're dealing with the force of gravity, like maybe this is the moon, or maybe this is the earth or the sun, heavier masses that are closer together result in stronger gravitational forces, okay, whereas lighter masses that are farther apart cause weaker gravitational forces. Okay, so if you're looking at the gravitational force for the sun that has a ton of mass, then that's going to make the gravitational forces that things attract to it stronger. Okay, it's going to pull harder on things compared to something small like a pebble. The gravitational forces from something as light as a pebble is probably going to be darn near unnoticeable. You wouldn't even be able to tell it's pulling on anything. Okay, also depends on distance. So the gravitational pull on the moon from the Earth would be a lot stronger if it was closer. Okay, and if it was a lot farther away, it'd be a lot weaker. So the fact that the moon can continue to go around and around and around the Earth without, flinging off into the distance or being pulled towards the Earth's surface and crashing into us is a nice little balance between that distance of that gravitational force, okay, being far enough that it's not being dragged towards us, and so the force is weak enough so it's not being like just crashing into us, okay, but also close enough that it doesn't just go like kind of drifting off away from us. So the force isn't so weak that it doesn't stick around near the Earth. Okay, electric forces work in some similar ways, but okay, there is kind of a difference. We can have charges that not just pull each other, they can also push on each other, which is kind of different. Okay, so with electric force, we have a similar thing where more charge or a higher charge, like a +1 or a +2 or a +3, the bigger that number gets, the stronger your charge is. Okay, and that can also go for negative charges. Doesn't really matter whether it's positive or negative. In terms of strength of the force. So, like a -3 charge is going to have a stronger pull than a +2. It just depends on what number is bigger. -3, +3 is stronger than a -2 or a +2, which is stronger than a -1 or a +1. Okay. And when those charges are closer together, those forces get stronger. Okay, that means that if you have a lower charge or a smaller amount of charge that's farther apart from each other, you end up with weaker electric forces. Okay. Now again, gravity always pulls things towards each other, but electric forces can also push each other away. Okay. They can either attract or repel each other. So opposite charges, like a positive negative or a negative positive, attract each other. They pull each other closer together, kind of like what's going on over here with these arrows. Okay. And like charges are the same kind of charge, like a positive positive, like here, or a negative negative, like here. Okay. Push each other away or repel each other. Okay. So unlike gravitation, we can actually have objects not just pull each other closer, but also push each other away, depending on whether your charge is positive or negative. Okay, so here we have a set of balloons. We have a balloon with a positive 3 charge and a balloon with a negative 1 charge. So they're attracting together because they're oppositely charged. We have a stronger force because we have this positive 3 charge really pulling them together. Again, you can try this for yourself. Get out of the way. Okay, so we've got some charges here, and you can pick them up and move them around and see how they affect each other. These lines are showing forces in the electric field. Okay, so if I take this charge on the right and I bump up its charge to like a positive 4, you'll see more lines coming out. We have a stronger electric force that's going on here that affects the other charge. Okay, if I bring this one down to a weaker charge, you see less and less lines. And if there's no charge, if it's neutral, it's not positive or negative, there's no field lines coming out of this at all. I can also turn this negative, and we have kind of the lines going into each other, so they can start to attract each other. Okay, and you can see this best if you change this over to hanging balloons, okay, where they kind of start to drift towards each other. Like if I set this back to a negative 1 and a positive 1. Yeah, I mean, they do kind of get closer to each other. If I step it up to a positive 2 and a negative 2, they start getting even more close together. If I make it a positive 3 and a negative 3, they're like really attracted. I can like barely get them away from each other. Okay, so electric charges can attract and repel. I gotta change my mouse back to classic. Okay, last page here. Okay, your charge is going to be conserved. Again, whether you have a net charge of 0 or a positive 1 or a negative 1, all those positive and negative charges are still there. It's just we can kind of ignore some of them if they kind of cancel each other out. Okay, and a lot of them end up doing that because we're made of atoms that have a very similar number of positive and negative charges. Okay, but we can still move those around. Even if something is neutral, we can kind of shift around the electrons of atoms to make them a little bit more positively charged, a little bit more negatively charged as we kind of take them from place to place. Okay, to get electrons to move, or in general charged stuff to move, we need something that is a conductor, okay, that allows stuff to move freely. Okay, a lot of stuff like this that are conductors end up being metals like copper and aluminum and gold and steel. You can also get whole ions to float around that have charge in salt water, which is why salt water and tap water can conduct electricity to an extent. Okay, the opposite of conductors are insulators. Okay, they hold tightly onto their electrons, or their charged particles aren't going anywhere, which means that we can't get them to move and flow. Okay, so good examples of this are rubber and plastic, air and wood. All right. Charges can be moved around in a couple different ways. One of the ways is by friction, or by the triboelectric effect. Okay, so if you have something like comb or a balloon, you rub it on a surface that has charge, you can sometimes kind of pick up that charge. So as I comb through the cat's fur, I pick up those negative charges. Okay. You can also see this, with a balloon rubbing against your hair, but this usually comes from two insulators rubbing together. Like this comb is made of plastic, and this fur or your hair is not really a great conductor of electricity. Okay. You can also move charges by contact. So when things are touching each other, you can have an excess of charge kind of move from one place to another. And you can also charge things by induction, where you kind of cause a push or a pull in something else without needing to touch it. Okay, so to show the contact, okay, this is showing what happens when you touch a Van der Graaf generator, which generates sparks. So here, let me mute it. We don't need the sound. Okay, so down here is this metal orb that is generating charge, which causes her hair to kind of move apart from each other. They start to repel. Okay, and that's because she's in contact with the metal sphere she's holding right there that's building up charge. So that kind of excess charge ends up moving somewhere else and causes her to have a little bit more positive or a little bit more negative charge. Okay, and to show our induction, we've got a charged object here. Okay, so maybe it's a plastic rod or a glass rod or something like that. We're going to bring it close to these. Right now, we have the rod charged with negative charges, and so as we bring it closer to this, you'll notice that the conductor kind of ends up with the negative charges pushing away from each other. So for the most part, they get away to the other side, leaving the positive charges closer to this negatively charged rod. So the positive and negative are attracting, the negative and the negative are repelling each other. Okay. For the insulator, you'll notice that the electrons can't really move much of anywhere, but they kind of push away a little bit. You notice kind of the circles start to turn to ovals. Okay, so we can still kind of induce a charge in an insulator, just not as strong as in a conductor. Okay, so if we have charge that's already built up that conducts and spreads out to something that's in touching it and it's in contact with it, that's our contact method of charging something. Okay, we move charge from some place to someplace else. If we rub together insulators and cause that charge to separate from each other, leaving one thing positive and making the other thing negative, okay, that's charging by friction or the triboelectric effect. And if we can cause that push and pull from a distance, we can separate the charge, or the fancy science word for that is polarize it, and that's called induction. Okay. Now, once you have a lot of charge built up, you can get that charge to discharge. Okay, in other words, you can move that charge away, so you no longer have a big buildup of positive or negative charge. You kind of spread things out so you get closer to neutral or totally neutralize something. Okay, so your electrons are going to quickly jump to an object with less negative charge. Since our electrons are negatively charged, we need something with less negative charge to kind of pick up those electrons, to kind of spread it out a little bit, to share it. So down here we have John Travoltage, which you can see in your own simulation, where he builds up some negative charge by rubbing his feet on the carpet, and then that extra electric charge is thrown somewhere else, wherever he can kind of share it away to. So in this case, it's a doorknob. So he has excess charge, and then he zaps it over to the doorknob. And I guess I actually have these pictures switched. I need to switch those around. So I guess technically he charges up first, and then he zaps the doorknob to discharge that extra charge, that extra set of electrons. Okay. You can actually see this as a spark if the room is dark enough, you have enough charge moving from place to place. As the charge jumps from place to place, you can sometimes see that as a spark. Okay, and again, you can check this on the simulation for yourself. So here's John Travoltage. You can charge up with his foot. You can move his hand around. Okay, so once you're close enough, you can pass the charge along. Okay, even if you're not totally in contact, you can get that excess charge to jump. Okay, so that's our introduction to charge.